Thank you, everyone, for joining us today. My name is Laura Masterson. I'm the community manager here at Typesafe. I'd like to introduce my colleague, Roland Kuhn, who's the Akka Tech lead at Typesafe. He's going to be presenting the Akka Streams presentation today, and also Konrad Malowski, who's a software developer here at Typesafe, is going to be assisting me with the Q&A. But before I hand things over to Roland, just a few housekeeping items. First of all, the webinar is going to be recorded, so if you have any questions throughout the presentation, please just submit those into the question pod, or raise your hand, and we'll do our best to monitor that so we can respond to your questions. We're going to be posting the recording on our YouTube channel as well as our blog shortly after this wraps up, so if you need to hop off early, don't worry, everything's being captured. And we're going to try to preserve some time at the end of Roland's presentation for a Q&A. So like I said, submit your questions, and hopefully we have some time to get to those at the end. If we're not able to get to your questions, we're going to be following up with you directly via email. So we want to make sure that all of your questions are answered. So with that, I'm going to hand things over to Roland. Roland, I think you can go ahead and share your screen now.
Is my screen shared?
Yes, it is.
Okay. Hello, everyone. This talk is not actually about Akka, at least not mostly. Akka will appear at the end. The presentation is about a project, a joint venture between several different individuals and engineers from different companies who all discovered along the way that they had the same problem, and that led to the Reactive Streams project to be formed. So I will talk about the problem that we are solving, where we want to go, the design rationale behind the solution that is currently forming. It's a project which is still in progress. And then I will, in the end, show you also some code examples on how that can look like. So first, one thing we need to talk about is what do I mean when I say stream? So what are streams really? A stream, the first thing is it is an ephemeral flow of data. Heraclit put that very fittingly. You cannot step into the same river twice. And the same is true for a stream of data that is flowing through your application. The point there is that you get data elements as they become available from the stream, and then you do something with them. So the second point is that when dealing with streams in your program, you focus mostly on the transformation of the stream, or of the elements. So you apply like rate transformations, or you buffer or drop things, or you transform them, decoding them, encoding things, and so on. And the third one is that a stream can be a live stream from some source which never ends. So it can be possibly unbounded in size. Common use cases of streams are, well, the first thing you think about is video streaming, probably. That's what I would call bulk data transfer. If you hop on Netflix and watch a movie, that's what happens. Netflix is not yet using Reactive Streams for that, but that is a use case we definitely had in mind. Then another common use case for streams are, for example, measurements or monitoring data, which are real-time data sources that provide values on their own, or that can be queried as you need them. And these data sources provide elements that can be arranged in time, and that is a stream of these values. Another example for such a real-time data source could be stock tickers, for example, from a stock exchange, or the trades which go into a stock market, and so on. There is one interesting connection between streams and big data as well. Namely that when you transform or batch process large data sets, what you write down focuses also mainly on the transformation of your data, which means you take in the whole data set, conceptually and produce some resulting new data sets or results from it. And the way this is written down usually shares a lot of similarity with how you think about and how you structure stream processing. One example where this similarity is extremely obvious is if you look at the Spark project, for example, which models the processing of big data as streams directly. Another use case for streams is monitoring and tracing information which you get out of your application. The qualitative difference there is that in that stream, it might not be important that you get every single element. You just want to keep up to date some dashboard, for example, displaying things. So you stream the actual performance values from your application, for example, to some other application which enables your ops personnel to monitor things and run your data center. Now, what is so special about streams that we call them reactive streams? What are the requirements? First, a little reminder for those of you who have not yet looked at Reactive Manifesto. When we say reactive, we mean this combination of 4 traits. And these traits are merely desirable properties that your program or your service or your component of a program shall exhibit. Topmost and most importantly, what a program or a service needs to do is it needs to respond in a timely fashion, and that is what we call responsive. Responsiveness means that you need a response from the service in order to determine whether it is up and running and to get the value out which the service is supposed to provide. And you need to do that also under circumstances which are not favorable. For example, you need responses as well in the face of failures. Your hardware or software could fail. And in order to get responses out, your application needs to be resilient. Resiliency means to recover the pre-configured form after a deformation. So to snap back into functional mode after having experienced a fault. And resiliency is therefore responsiveness in the face of failure. On the other hand, when you implement an application that you offer services with on the internet, you will experience that the load which your application has to handle varies greatly. It could start out very small, for example, and when your little application becomes known and becomes used by users, then, well, the load will rise dramatically, hopefully, because that means you're successful. But it also means that your service will need to withstand a much higher load suddenly. And in order to stay responsive in the face of varying load, the service needs to be scalable. All of these traits, in the end, require the implementation to be based on events, reacting to events to make all this possible. But how does all of this apply to streams? Well, if you want to achieve resilience, then you need to encapsulate and distribute your problem. Because if one component handles it, then that component becomes a single point of failure. So you will have to distribute. You must avoid to put all your eggs in one basket. So you encapsulate and you isolate and you distribute. Encapsulation and isolation means that you have 2 components which exchange some data, but you don't want to couple them synchronously. You want to send messages from one component to the other and let that other component react in an asynchronous fashion. This means that resilience basically demands asynchrony in your programming model. It becomes quite obvious when you think about distributing across different network nodes, because all network communication is at the core asynchronous. On the other axis, when you want to have scalability, you will also needs to distribute, because every piece of hardware that you buy has a certain limit, a certain maximum capacity for the load that it can handle. It could be memory constrained or CPU or anything, but none of the resources are infinite. And therefore, when you want to scale beyond what a single machine can do, then you will have to distribute your program. And distribution, again, means asynchronous communication between the parts. So the problem statement has something to do with asynchronous boundaries. Just let me enumerate a few of these here so that you have a clearer picture in your mind what I'm talking about. So if you have different applications talking with each other, then they will need to exchange data asynchronously. One application does not simply synchronously call a method of another application. There is some sending of bytes involved in either direction. The same goes for exchanging data between network nodes, obviously over Ethernet, for example. But if you follow the current trends in hardware design, you will notice that within a single machine, we also have a distributed system nowadays. We have multi-core CPUs, where the individual cores communicate via their shared L2 and L3 caches. But in server hardware, you typically have different sockets with CPUs in them, and if a core on one socket wants to communicate with the core on another socket, it will have to go over something like a QPI link, for example, and that is very similar to a network transfer. In fact, the performance characteristics, so the latency and the bandwidth available, are nowadays not that far from each other anymore, so we need to consider a system which is distributed across different CPUs already as a distributed one with asynchronous boundaries between the participants. Then obviously, if you want to pass data between threads, that is an asynchronous boundary. You will typically put your data into a queue to be picked up later as an asynchronous action by the receiving thread. And breaking it further down, looking at Akka, for example, if you pass data between different actors, where multiple actors can share one thread, so in that sense they are smaller than even threads. If you pass data between actors, that is also an asynchronous boundary, because all interactions between actors are asynchronous by nature. So the problem statement for reactive streams is, how do we get data across an asynchronous boundary? There were several solutions which have been tried in the past. Let me call the first one the traditional way. This means that you have blocking calls. So you have a blocking queue, for example, between two threads, and when the receiving thread is too slow, then the sending thread is simply blocked and it cannot do anything else. But this is not a very reactive system which you then get, because the sending thread being blocked means that it cannot react anymore to anything, not to cancel requests, not to newer events which might come in, and so on. Imagine, for example, you want to pass data from one thread to the other of a stock ticker, and if the recipient is not fast enough, you just want to throw away the old data and keep on forwarding the newest one whenever there is time. If you would just use a blocking queue to do that, then you would have to think hard how to achieve this, this scheme. And the other thing is, blocking threads is really bad for CPU performance, because it means that you will incur context switches, or your CPU might go into a low power state, which means that after the blocking period, so when the thread wakes up, everything will be quite a lot more costly. So we want to avoid blocking threads. So the traditional way is not something that we want to do. Now, we could think of a way that frees the sender, that makes it completely oblivious to the recipient. This is the pure push way. if you only push data from sender to recipient, then the sender can always do that without concern or anything. But at the recipient side, you might get the recipient might get overwhelmed by the amount of data. So what it needs to do is either it needs to buffer things, or when it can't buffer anymore, it needs to drop things. And that means that it's either lossy when you drop things, or if you do unbounded buffering, then you run the risk that your system will run out of memory. You get an out-of-memory exception in the JVM, for example. So this goes in the right direction, but it's also not quite the thing that we wanted to have. So what do we do now? Well, we just postulate that there is a reactive way. And what we want is, we want it to be non-blocking on the sender, on the recipient side. We want it not to drop things automatically. So we want dropping to be a conscious choice if we need it. But the mechanism itself should not require dropping. But still, we do not want to run the risk of out-of-memory exceptions. So how do we do that? Well, it sounds magical, and it sounds like we postulate something which we can't really fulfill, but think about it. TCP has been doing something quite like this for a few decades already. And the recipe is basically that we need to match up supply and demand. The trick here is we call the sender a publisher and the receiver a subscriber. The trick is that data items flow downstream, but only if enough demand is flowing upstream at the same time. So the subscriber, which is sending the demand, can control exactly the data rate which comes flowing at it. And this also means that the number of data items that can be in flight at any given point in time is regulated by the outstanding demand that the subscriber has signaled. So when the subscriber initially says, give me 5, and then the publisher sends 1, sends another 1, and that's 3 outstanding, so it can send another 3. But then the publisher needs to stop sending things because there is no more demand. And when the subscriber finally demands more, then the publisher will eventually send more. This is a very simple scheme, which is kind of like the TCP acknowledge mechanism, but it is more focused on complex data items and brought into the application level where this is all very accessible. Now, if you look at the behavior of such a system, you might ask yourself, is this push or is this pull? And the question depends really on which of the two parties is faster. Because as long as the demand is always big enough, so the subscriber is faster than the publisher and signals demand, it says, give me 1,000 and give me 1,000 and so on, and the publisher will never run out of demand. So whenever the publisher has some data which it wants to push down, it can do so. It's a pure push model, but that turns around when the subscriber falls behind. When the subscriber has no further demand signaled, the publisher will eventually stop sending data. And when that happens, the publisher will accumulate data, presumably, or at least the ability to get data over time. And the next time the subscriber sends some demand, the publisher can immediately respond. So this turns into a pull model. So those are the two extreme cases, and the system switches between these situations automatically, and it adapts. So it can be a mixture of both, so that when the demand is signaled, you pull items out of the publisher. The publisher might not have them all handy, so they might come a bit later, and so on. So it should be a nicely self-balancing model. Another property of this is we thought about batching. Why is batching important? Well, CPUs today are optimized for basically one thing. They are at their best when they can do the same job repeatedly, like millions of times in succession. That will be optimal, when they can predict what will happen next. And then caches and everything are most effective. Now, by allowing the demand which is flowing upstream to be batched, so the subscriber can say, give me 1,000 instead of 1,000 times saying, give me one. Then the publisher can just churn out 1,000 data items and send them towards the subscriber. So the publisher will very efficiently publish them. And normally, the subscriber will also get them, these data items, into quick succession. If it runs on a different CPU or machine, or if it runs on separate computing resources, it will probably also very efficiently pull these data items from the shared medium out of the queue, for example, or from the network. So the batch demand can be used to apply batching also to the data. Now, in this model, we have two data streams, which are flowing in opposite directions. Data flow downstream, demand flows upstream, and they are explicitly modeled. They are explicitly described as the two sides of the same coin, basically. And when you do that, and when you have access to these values, then you can do interesting things. For example, consider a publisher which splits a stream to two subscribers, as is drawn here. So the data gets split, or they could be copied, could be broadcast. Then both subscribers will have to provide their demand tokens, the demand streams. And the publisher can then merge these demand streams in any way that is suitable for the problem. So if you want to, for example, broadcast, then you will have to zip the demand streams. So both need to signal demand in order to, for data items to flow. But you could also use this for a round-robin router, and then you require the demand to be roughly equal in rate from all the subscribers. You could also use it for load balancing, so that each subscriber signals the demand, which is the rate at which it will get items. And then items will be processed by the subscribers according to their processing resources that they have available. So what you see here basically is, as I write, splitting the data means merging the demand. You can flip that around easily. It's all symmetric. Merging the data streams means splitting the demand. So when you want to merge two streams together, you can, since you explicitly handle the demand in the subscriber in this case, you can tell each of the publishers to go ahead at the rates which you want to allow them to. So in the end, being explicit about demand propagation in this model allows very interesting choices concerning flow control and the handling of multiple streams. So a summary for this part, reactive streams basically are all about crossing an asynchronous boundary, which means that we have an asynchronous non-blocking data flow downstream. We have an asynchronous non-blocking demand flow going upstream. And by structuring it such that we allow batching and so on, and minimal interaction, minimal synchronization between the parties, we reduce the coordination and contention overhead and allow very efficient very hardware efficient implementations of this scheme. And the important one is that, well, data items are messages which flow downstream, and demand are messages which flow upstream. And messages can be passed across different media without any influence on the semantics. So you can apply this model across all kinds of asynchronous boundaries that I've highlighted initially. So between applications, between network nodes, CPUs, threads, actors, and so on. Before we can get to the meat, and before I can show you code, I would like to take the opportunity to look at a rather interesting question, namely whether streams are collections. When I researched this, I found it hard to believe that it's so difficult to get a good definition of what is a collection. If you look just into the Oxford English Dictionary, a collection is a group of things or people. This means, for example, all attendees on this webinar would be a collection. And the point there is, it's kind of a known group. So you know who's in there, you know how many there are, and so on. If you look at Wikipedia, what it says about a collection in computer science, it says it's a grouping of some variable number of data items. Again, that's the same concept as expressed in the natural language dictionary. Then I didn't find that many references, so I just include one I found here. In the documentation for Backbone.js, I found that collections are simply an ordered set of models, which also fits the thing that it's a group. It's kind of a known, it's a set of things. And finally, if we look at what the JDK has to say in this regard, Java util collection is an interface which has certain methods from which we can draw the conclusion that a collection has a definite size. So it has a size method which returns an int. It provides an iterator, which means you can enumerate what is in the collection. So it is a certain number of items which you can all find out about. And you can query for membership. It has a contains method. Now, when you say collection to a developer, then there are certain expectations which come with this. So if you iterate over the elements of a collection, you certainly expect to visit all the elements at the given time. So you might have heard that if you just use a normal collection from multiple threads, you might have problems. But that aside, if you have a collection in your hand, especially an immutable one, you can just iterate over it, will see all elements. Now, if you have any sequence, like a list, for example, and you take the head and the tail and you put them back together, you expect the result to be, well, the full list, which goes into the same direction, saying that you can treat a collection as a static thing, which you can statically reason about. Another feature of a collection is that the contents of it are fixed. So it does not depend who or which piece of code it is that does the processing. Neither does it depend on when the processing happens. You can keep a reference to your collection, and especially if it's an immutable one, it will never change. So you can process it next year and it will have the same result. Contrast this with streams. Streams, as I said, are these ephemeral things. You can't step into the same river twice, and so on. So it depends very much on the observer, which sequence of events, which sequence of items is seen. First of all, the stream might have begun flowing before an observer subscribed, so you might miss a certain prefix of the stream. And then we have seen that observers can, for example, be not fast enough, in which case, well, if it's a stock ticker, for example, which you can't slow down, and you have a consumer which consumes it, and the only choice when the consumer is too slow, well, you need to drop data somewhere, which means that this observer will not see all elements that were in the stream. It could also be the opposite, that you have a stream which is not fast enough, but which you are kind of filling the gaps in. So you want one measurement per second, but the device from which you get it does not every second generate one. But you can still create a stream from it which gives you the current value every second. So streams are a bit surprising in some respects. Now, this brought me to the conclusion that streams are not good collections. We should not say that they're collections. And the Java util stream package, which was added in JDK 8, seems to agree with me in multiple ways. First of all, the stream interface is not derived from collection. So in that sense, it is not a collection. And the documentation also says that streams differ from collections in several interesting ways. First of all, the no storage. That means that you don't keep the whole stream in memory. That's the ephemeral part. then focusing on the transformations instead of the elements, so functional in nature. And the Java util stream especially is laziness seeking. So you define how you want to transform a stream, but that does not actually run anything. Instead, it gets run only when you invoke a so-called terminal action. Streams can be unbounded. We have seen that collections, at least in Java, have a finite integer size. And especially with the Java streams, they are consumable, which means that when a stream has run once, it is gone. The stream has flown, and it's not there anymore. You need to create a new stream if you want to process it again, if that is even possible. So for these reasons, I maintain that streams are not collections. We shouldn't say that. Of course, a collection can be streamed. So you can take the elements of a collection and feed a stream from them. And the opposite is also possible within a stream observer, within any of these subscribers, for example. You can add elements as they come into a collection, and thereby you can create a collection from a stream. But still, a stream and a collection are not the same thing. So we should not say that a stream is just a lazy collection. So, coming back to reactive streams. Of course, we looked at technologies that exist for solving this problem of getting data across an asynchronous boundary. So I'm going to show you two choices in the following. So why not just use Java util stream, the package and everything which is in there? If you look at it, this is how you can do it in Java 8. So here I create a stream of the three values 1, 2, and 3. Then I describe a transformation of it by applying the map function with a lambda expression that prepends the letter A, the string A to the integers. So it will be A1, A2, A3 in the stream. And then we have basically two basic choices. We can call .iterator on it, which will convert this into a poll collection, where we can use the normal hasNext and next methods to get things out. Or alternatively, we can just push it somewhere. The for each combinator in this case will run the stream, and for every value which is encountered, so A1, A2, A3, it will call system out println and show it on the screen. As I said, in Java 8, the streams are consumable, so the code as written here will not actually work because the two things which you can do are exclusive. You need to pick one. And if you want to process these elements 1, 2, 3 again, you need to create a new stream of them for the second time. In summary, Java 8 stream provides a DSL for describing transformation. And interestingly, it introduces staged computation. So you describe the transformation that you want to happen without them actually happening. They only happen once you actually run the stream. But the problem there is that the Java util stream package prescribes an eager model of execution. That means when I call the for each method on a stream, it will run it. And the thread on which I do this will be blocked until the stream is fully processed. So the for each method only returns once the stream processing has fully finished. And the other problem is we have seen that what we would like to have is this dynamic push-pull, because we don't know whether the consumer or the producer is faster. But with the Java 8 streams, you need to decide early on whether you want to push or pull. You need to do so statically, which is not that nice. But I think the Java streams will evolve over the coming versions. So there is one other candidate, you might have heard of it, and that's RxJava. It's a port or inspired by and further development of the reactive extensions for .NET, which were done by Eric Meyer. And he has done, together with Netflix, the port to the JVM called RxJava. So how would this problem look like in RxJava? So here we can create the same stream. It's a range from 1 to 3. and we map it in the same fashion, just appending the string B to it. And one difference to the Java 8 streams is that you can actually use it twice. So this will really work. You subscribe a piece of code to the stream, which will make it run. And this will, the first one will print out B1, B2, B3. The second one shows that you can apply another filter to it, for example, and then print out, and then it should only print B2 in this case. Java implements the pure push model, as discussed, and it includes a very, very extensive DSL for transformations. You should go look at the documentation, which is on GitHub in the RxJava wiki. They have these wonderful marble diagrams which show how elements flow when you mix different streams, you concatenate, merge, and what you can do. So it has really a lot of combinators for expressing everything that you might want to do with streams. It has only one or two flaws in that previously it only allowed blocking for back pressure. So it's a completely synchronous model in that sense. You call on next from the observer, you call from the observable, you call on next on the observer, and the only way to slow down the observable is by blocking in that call and consuming time on that thread, so to speak. The other, so it has combinators for passing across asynchronous boundaries, but these combinators currently use unbounded buffering on the receiving side, so it can go out of memory. And these issues precisely sparked the beginning of the Reactive Streams project when I was in Lausanne with Eric Meyer and discussed things in front of a whiteboard. Because he was working on remote observables at the time, and that kind of piqued his interest at about the same time that we in the Akka team had a very similar problem. This brings me to the Reactive Streams project. First of all, this is not a Typesafe thing. It's a collaboration between different companies, different engineers from these companies. I put them in alphabetic order. You can read, so there are people from Netflix, Oracle, Pivotal, Red Hat, Twitter, and Typesafe, and some individuals like Doug Lee of Java Util Concurrent fame, and Todd Montgomery from Kazing. So all of us discovered that we have a common problem, namely how to pass data, streams of data, across an asynchronous boundary. So we thought that everybody would profit from building the tools and solving this problem once. And the goal is that we will have multiple implementations of a common solution, and these multiple implementations should smoothly interoperate. That is the core motivation behind the Reactive Streams project. I've listed here a completely made-up scenario where you use data store driver from Reactor, stream the data through some Akka-based transformation pipeline, and monitor it using Rx, and the whole thing drives a Vertex REST API, for example. This does not yet work, but the goal is that one day it will. So how do we make this effort successful? First of all, we strive for very minimal interfaces. So whatever an implementation of the Reactive Streams specification must provide should be rather simple in terms of Java methods. The footprint should be minimal. But on the other hand, everything, the semantics of these methods should be very closely specified, very rigorously specified. And to make this really useful, we require also a full TCK that can be used to verify every given implementation. On the other hand, while the specified interfaces are really minimal, we completely stay out of the business of prescribing what the API should look like. So how you transform your streams. You could use the Java 8 Stream API to do parts of it. You can use RxJava. You can use Java 6 or Java 8 favoring APIs or Scala APIs, Groovy APIs, whatever you want, because that is not part of the standard. And we took care to allow efficient implementations independent of the language. Now, what does the code look like? Everybody has been waiting for this, I guess. It's basically just 7 methods. 7 methods in 3 interfaces. We have a publisher and a subscriber, and the subscriber hooks up to the publisher using the subscribe method, which creates a subscription. And in the end, the back pressure mediation happens between the subscriber and the subscription. I will show you how that works in a second. But please take note that all these 7 methods return unit. And that is on purpose very much, because it allows their implementation to be completely asynchronous. Having a different return type than unit would mean that something would need to be constructed and returned on the spot. And if you have an asynchronous boundary, which is, for example, one end is living on one node, one network node, and the other end on the other one, then anything but unit would require a network round trip. And that is something we do not want to require. So this is why everything returns unit. Now, these methods are the interface, and then the specification is a lot longer than what I've written down here on this slide, but it boils down to basically this. Everything must be async. It's an asynchronous boundary that we're crossing, so all calls on subscriber must dispatch asynchronously, and all calls on the subscription must also not block the subscriber. And basically, the publisher is just there to get the thing going. It doesn't have more function than that. It is basically not really specified where the stream comes from, because the spec is only about how does a stream get across an asynchronous boundary. So how does the setup of a stream between publisher and subscriber work? First of all, the subscriber gets passed into the subscribe method on the publisher. The publisher then creates a subscription, which is passed back into the onSubscribe callback of the subscriber. And this two-way handshake basically introduces both parties to each other. Now they both know about each other, and the subscriber can from this point on request more data by calling the appropriate method, which is probably going to be renamed request. There's an outstanding pull request for that. But that's a detail. So request more is called with, say, 5, and then in the following, the subscription may call, or the publisher may call on next 5 times on the subscribers. And this is how the stream starts flowing, and it goes on from there. The stream can terminate either with on complete or on error, which are terminal actions in that sense. So after that, the stream doesn't exist anymore. Now, this was the generic part talking about the Reactive Streams project. I will spend a few minutes on one particular implementation, namely Akka Streams. First of all, Akka Streams naturally are powered by our actor implementation for the execution of all the processing of streams and the possibility of distribution. And we will also make use of supervisor hierarchies to achieve resilience. The way we got into this effort is maybe also interesting. So the problem that we have seen on the mailing list was that people wanted to pass data from one actor to the other. And the usual thing which happens in the beginning is that you get an out-of-memory exception because your mailbox blows up. So you need to implement flow control yourself, which yeah, can be non-trivial. And what people also complained about a bit is that actor messaging currently is unityped. It's tell accepts any. But if you could have an abstraction on top of that, then you can have type-safe streaming of data through actors. Now, getting into the meat of it, this is how some code using Akka Streams could look like. So here, the DSL which we have chosen is based on the flow keyword. A flow describes the transformation which shall happen in the future. It's like you can picture that like you have this faucet from which you can, when you open it, the water will flow, but it's still closed, and you connect some piping, some ducts, and so on, which are still dry at this point, but which describe where the water shall flow. And then in the end, with the so-called terminal action, that will be on complete here, you open the faucet and let it flow, and the water then flows through the setup that you have constructed beforehand. Now, the setup which we have here does the following. It takes from some text, splits from some string, split into words. It creates a vector of strings, which are the words in this text. And then for each of these words, it applies a transformation. It maps all to uppercase. And then for each of the transformed words, it invokes print line. Then finally, you might wonder, for each typically does not return anything, but in our case, for each does return a stream of unit, and it emits exactly 1 unit value when the whole processing has stopped. So this stream needs to be consumed in order to run the whole thing, and that's done by the onComplete combinator. So when it successfully terminates, so none of the interactions in between has done on error, then it will shut down the system. Otherwise, if there was an error, then, well, it will print a failure message. There's one thing which I have left out so far, namely, where does this flow live? I said it's based on actors. So we will have to create an actor system up front. And then this flow DSL needs a flow materializer called MAT in this case. And this flow materializer decides how the actual actors are created and how the transformation steps are allocated to actors. The default flow materializer, which we have right now, will allocate 4 actors for this case. First, for the initial streaming from a vector, that will be 1 actor. The map operation will be in 1 actor. The for each will happen in 1 actor. And the onComplete will also happen in 1 actor. This means that all the actions can run nicely in parallel, and we can use as many CPUs as we have in our system. The interesting part is that we foresee this flow materializers from the beginning because we know that we want to maybe optimize this further down the road. So for example, we could have a flow materializer later which fuses these operations and runs them all in 1 actor. Or we could have one which implements them in a completely different fashion, or which runs them on different cluster nodes, which it currently does not yet do, or yeah, whatever you fancy. So the flow materializer is what makes the physical representation of the stream very flexible. The flow just describes what happens, and the materializer how that happens. Here I have a more juicy example, if you will. The only new thing, you don't need to understand all of it right now. This is on the activator template. So what this does is it splits a file into different log levels according to a log level pattern. And the interesting feature here is that this produces a stream of streams, or precisely a stream of pairs of value and stream. And so the level is the value, the producer is the new stream. And then we produce these different substreams to different files on disk. You can try that out later. I will give you the link. Then, of course, we have also not forgotten about Java, and Java 8 makes this really nice. This also works in Java 6, but it's more verbose, obviously. But in Java 8, it looks basically as nice as the Scala version. So we create a flow from a string of integers and transform it in various ways. So you can read and ponder this on your own time. The interesting part is that Java 8 actually makes Java usable for such use cases, where you have lots of these small functions, which used to be anonymous classes in Java 6, which basically made this look very verbose and ugly. One last example from the Activate template is a TCP echo server. So we have a stream TCP IO extensions here, which you can ask to bind to an address. And this is all just boilerplate here to print when we are listening and what the local address is or when it cannot bind. The magic happens in these 4 lines in the middle. So the server binding, which we get back here, has a member connection stream. And incoming TCP connections will come out of this stream. And for each of these, we take the connection C, we print the address of the client from which it came. But then to make an echo server, the only thing we need to do is we take the input stream of this TCP connection, and we say produce to output stream. And that simply puts all inputs back into the output, and we have an echo server. Pretty neat. One thing which I should have done, which I have not yet done, is put in the code from the Akka HTTP work, which is currently being done by the Spray team. It should be possible to fit the central pipeline definition of a complete HTTP server basically on one slide, if I'm not mistaken. I'm very excited about that development, and you'll see announcements in a few weeks. But here is still an HTTP sketch, which is not at all real code. So we have an HTTP extension from which you can get a channel set up. You can create a flow from a file and use that as a body of an HTTP request, which is sent to some address, and then you get a flow back from this channel that you requested, which will contain the responses from the web API, for example. And then we stream these responses into a sync, for example, a file. But this is a pure sketch. You will see real examples real soon. So closing remarks, and then I hope we have some time for questions. The current state of this project is that we have early previews available. For the Reactive Streams, it's version 0.2. And for the Akka Streams, the implementation, we have version 0.3. But expect these to change possibly substantially over the next months. It is very active in development. You can look at the Akka Stream example by checking out this activator template, Akka Streams with Scala, and the code is on GitHub. But the main point is that we are working towards inclusion of this Reactive Streams project into a future version of the JDK. So the most awesome thing you can do is to try it out, look at the specifications and the descriptions on reactivestreams.org and the GitHub organization on this slide, and participate and give feedback and open issues. Thanks a lot.
All right, thank you so much, Roland. That was wonderful.
So,
can you hear me okay?
Yeah.
Okay, great. Just wanted to say thank you to you, and also for everyone who joined. Hope everyone found Roland's presentation helpful and informative. We've had a lot of questions submitted, and Conrad, who's been manning the Q&A session, has been doing a great job responding to people in real time. I just wanted to kind of lead with a couple questions that that he's called out, so that everyone gets a chance to have Roland hear the response. So the first one is, so with regards to Reactive Streams, how can a subscriber figure out when to ask the publisher to send more messages?
So the idea of the setup is that the subscriber should signal how much it is willing to buffer. So when the subscriber has an internal buffer, say, of 5, then it should say, give me 5, and eventually up to 5 will come. And then it might be smart to start asking for new elements before the buffer is completely drained. The point there is that the subscriber is in full control and can steer the publisher in any way it wants.
Okay, great. Next question, would Spray support Akka Streams as well? I.e. can Spray REST EPs be streamed?
Yes. So as I said, Matthias and Johannes are working on porting Spray into Akka HTTP, and this work is completely based on streams. So the internal architecture of Akka HTTP will completely be based on streams, and these APIs, as one sketch I've shown, will also be will be exposed to the user. So you can stream your HTTP request bodies and response bodies and so on. Streams will be really nicely integrated with it. There's one question which we usually get, which is how does that all relate to Play? Play framework currently uses Netty, but eventually it will be ported over on top of Akka HTTP. And at that point, also Play will then start offering stream-based APIs for consumption to the users.
Okay, great. Next question, what if there are no subscribers yet, so the data is still flowing? Was decided whether to discard or store data streams?
That is dependent on the use case. So if you have a publisher which represents a data source that supports back pressure, for example, reading from a file, then, well, when there is no demand, then you simply don't read from the file. But if you have a publisher which represents, for example, mouse movement or stock ticker updates, then you can't slow them down. So when there is no one listening, you just need to until someone is really interested. The point there is that how a publisher works internally and how it generates the stream that it emits is really use case specific and not governed by the Reactive Streams specification.
Okay, great. I'm going to try to skip ahead to some questions that Conrad didn't get a chance to answer. So this question is from David Hoyt. What about conveying back pressure for streams that do not fit this model? For example, calling external HTTP services that when it is running out of resources begin to refuse new connections. How would that work when back pressure is implicit?
So the point of this proposal is that back pressure should never be implicit. It's always explicit. It's always managed. So when you have a stream pipeline, and within that, one step is to call an external service, then the rate of responses you get back from this external service will be translated into the back pressure that you insert into your pipeline. If you need to shunt that, for example, if the web service stops working, you need to take a different route, then you will have to reroute the stream, for example, or you will have to fail early the requests and react to things not being available. But those are things which you implement using and on top of Reactive Streams. Reactive Streams themselves are only concerned about explicitly passing along back pressure.
Thanks, Roland. I have one more question here, and then unfortunately we've run out of time, but we will make sure to address everybody's questions directly via email. So if your question wasn't answered, you'll hear from us soon. The last question here is there a Scala 2.11 release for Akka Streams?
Oh, that is an excellent question. That might not actually be the case. I will open a ticket right afterwards to do that.
Great. All right, guys. Well, thank you so much, everyone, for joining, to Conrad for handling Q&A, for Roland for presenting, and for everyone who joined us today. The recording will be available within a day or so, And as I mentioned, we will be following up directly if you submitted a question. Look for the recording on our YouTube channel, and we're also going to be sending out a link directly if you've for everyone who registered. So with that, I'm going to say goodbye and hope to see you on our next webinar.
Yeah, thanks, Laura, for hosting.
All right, bye guys.